Question 3. A particle of mass 5 kilograms rests on a smooth horizontal table between two vertical walls which are 8 meters apart. It is connected to the walls by means of smooth horizontal elastic strings. Both have got natural length 1 and elastic constant 20 newtons per meter. Initially the particle is held so that the right hand string is just slack and then it's released from rest. We want to show that the particle will perform simple harmonic motion. Now, because both elastics have got the same natural length and the same elastic constant, the equilibrium position O will be midway between the two walls. This means the distance from A to O is going to be 4 meters. Now, if the particle is displaced some distance S to the right of O, this means the distance from O to P would be S, which means then the distance from P to B is going to be 4 minus S. Now, when the particle is in position P, the two forces acting on it are going to be the tension to the left and the tension to the right. Now, if we want to find the force on the particle when it's at position P, now this force was applied to the particle to the right, so that means this force is going to be TR minus TL. Now, F is MA, the tension to the right is given by Hooke's law, which is K on L minus L0, and similarly, the tension to the left is also given by Hooke's law, which is K on L minus L0. So the mass is 5, the acceleration is A, the K value for both elastics is 20, and the length of the elastic to the right is 4 plus S minus its natural length, which is 1, and the length of the elastic on the left, L, is 4 plus S, and we need to subtract its natural length, which is 1. So if we multiply out the right hand side, 5A equals 60 minus 20S minus 60 minus 20S. Now the 60s will cancel, and 5A equals minus 40S, and this means A equals minus 8S, which means it does execute simple harmonic motion with omega equals root 8 or 2 root 2. Next of all, we want to find its maximum speed. So Vmax equals omega times A. Now, initially the particle was released when the right hand string was just slack. That means it was released at its natural length, which is 1 meter from the right hand wall. If it's 1 meter from the right hand wall, it's 3 meters away from O. So A equals 3. So Vmax is going to equal 2 root 2 by 3, and multiplying that gives 6 root 2 meters per second. Next of all, we want to know how far from the centre of oscillation will the particle be when it is 1/3 of its maximum speed. So we want to find out what S is when V equals 2 root 2. Now we know the amplitude A is 3 and we know that omega is 2 root 2. So here we're going to use the V-was equation. So A is 3, V is 2 root 2, omega is 2 root 2, and we're looking to find out what S is. So using the V-was equation, V squared is omega squared on A squared minus S squared. This means 2 root 2 squared equals 2 root 2 squared on 3 squared minus S squared. Squaring then 8 then equals 8 on 9 minus S squared. If we bring the 8 on the right across and divide with the 8 on the left, 1 equals 9 minus S squared. If you bring the minus S squared from the right to the left, it becomes a plus S squared. And if you bring the plus 1 over from the left to the right, it becomes a minus 1. So S squared will equal 8, and that means S is the square root of 8, or 2 root 2 meters. Next of all, we want to know when will it reach this speed for the first time. So we're going to be using the equation which represents the displacement after time t. S equals A cos omega t. Now we know the amplitude A is 3 and omega is 2 root 2. So this means S equals 3 cos 2 root 2 times t. Now we're looking to find out what the time is when S equals 2 root 2. So when S is 2 root 2, 2 root 2 is 3 cos root 8 times t. Root 8 is the same as 2 root 2. And if we divide across by 3, 2 root 2 over 3 is cos 2 root 2 times t. And then if you get the inverse cos of 2 root 2 over 3, that equals 2 root 2 times t. So if your calculator is in radian mode, if you get the inverse cos of 2 root 2 over 3, and then if you divide the answer by 2 root 2, this gives a t value of 0.12 seconds.